And the first thing that we're going to do is we're going to the OpenQuake engine. So we're going to double click on the blue and white icon, okay, to start the OpenQuake web UI. Remember the Mac users, you have to use the command OQ web UI start in your console. And that is going to bring us the OpenQuake engine, okay? So let's just give it a moment while it starts to open. You will see you can see it here. You will see the console starting to run in the background, and then you are going to see what I'm showing right here is my previous calculations. You can see the web view. Okay, so perfect. We have OpenQuake running in the background. Let's also start now the QGIS project. Okay, so thank you, Kata, to start OpenQuake. OQ web UI start in the console for those who are Mac users. So how do we start the QGIS project? Today we're using a different project. We are in a different region of the world. We have a PSHA model from a different region of the world. So what we're going to do is, in the material of today, once unzipped, okay, we are going to double click on the folder, and we are going to, you can see it here in my, let me bring this up. We're going to double click on the module 4, okay? So you in module 4 maps QGZ, so you double click there, and this is going to start the QGIS project of the work itself as well. So very good. I am right here. You can see this is the project for today. It's not Medellin as last time. This is not Colombia. I will explain a little bit soon where we are. Basically, this is Ecuador. What we're going to do is run the calculation, okay? Leave the calculation running, and then we see what we're doing. Then I will go back to the presentation and explain everything that we're doing today. So how do we run the calculation? Number one, make sure that OpenQuake web UI is running in the background. So make sure that we have this on, okay? So I can see it running in the background, perfect. We're going back to the QGIS. We're going back to the QGIS project, and we're going to use the plugin to run the calculation today. So in previous exercises, we have seen how to use the web UI. Let's run a calculation from the plugin today. We're going to click on the play button. This button right here is the little blue and white play icon that we have. I click on play. This is going to bring the the plugin interface that we can see right here, where I have my previous calculations there. Okay, perfect. Remember that this interface is analog to the web UI. What we're going to do is click on run a calculation. Okay, click on run a calculation, and we have two options. Look, when we're running a calculation in this way, and I think you saw this with Kendra, if we're using the plugin, when we click on run a calculation, we have two options, either to run a calculation from the directory or running a calculation from a zip archive. Today, we're going to run it from a directory, okay? And which directory it is? It is the directory of our module 4 exercise material. So we're going to click on OK. And I am going to go and make sure that I go to my material exercise. Mine is in the desktop. I go to M4 exercise, the folder that is called event-based risk, and I select that folder. When I am in this in M4 exercise event-based risk, I make sure to select this folder, and that is going to start the calculation. Okay, so I will repeat just to make sure that everyone can follow me. You click on the play icon, okay? So you click on the play icon, and this is going to bring you the plugin, okay? The plugin interface. You click on run a calculation, okay? And then you click on directory. You make sure that it's from a directory. You say okay, and then you navigate to today's exercise, M4 exercise event-based risk. And once you're in that folder, you just select that folder and and the plugin will identify that there is a job ini file there that it needs to execute. So it will read it and start executing it. Okay, so you can see that my calculation is running right now. If I open the console, you can see it's right there running. In my computer, it usually takes, I think, 15 minutes or something like that to run this calculation. We will see, but it is running in the background. So I am leaving this calculation running in the background, and I am going back to the presentation to talk about what we're doing today. In the interest of today, this is so we can finish within 1 hour and a half this exercise. So before we move on, I just want to ask, does anyone was unable to execute their calculation? Raise your hand if you were unable to execute the calculation of today. If it doesn't say executing, or if it says fail, or if you didn't find it, just let us know. Okay, I'm just giving you a small time. Very good. Okay, it seems like everyone is running the calculation successfully. I will let you know when my calculation is done, so you can more or less understand if you can check if yours is done as well. I am leaving this, and I am going back to the presentation. So I am going back. Perfect. So the example of today. What are we doing today? What is running in the background right now? We're still in South America, okay? Previously, we were more or less in a region of Colombia, very close to the in the city of Cali, in the South Pacific part of Colombia. Now we are in Ecuador, the neighboring country in the south, and we are in this particular province. Is this main province here is where the capital, the metropolitan district of Quito is located. It's a big city, almost 3 million inhabitants, a lot of heritage buildings, a lot of productive assets, a lot of people living in this area. So today we're providing you the exposure model for the province, okay? So basically we have, for the metropolitan district. So this is the metropolitan district. We call it the DMQ for short. So the city of Quito, or the metropolitan district of Quito, is divided in these different neighborhoods that we have right here. So your exposure model is for neighborhoods right now. So we just provided that that information. It's in the folder of today's exercise. And you can see here, basically, we have a lot of buildings in this exposure model. And this is the resolution, basically in the neighborhood scale. What is in this exposure model? So this exposure model contains a specific set of building classes. Okay, so we have selected these building classes out of the entire exposure for the city. And how is this exposure model composed? Okay, so basically we have, in terms of buildings, almost 60% of the buildings are masonry panels, okay, confined by small concrete elements with a limited level of ductility, let's say low seismic provisions, and most of them are 2 stories high, 3 stories high. This is making up almost 90% of the buildings that we have in the exposure model of today. In terms of replacement cost, you can see that again, like most of the replacement cost is dominated by these 2 building classes. And also in terms of occupants, you will see that most occupants live in these 2 building classes. So basically, individual houses, 2-3 stories, made of these masonry panels, semi-confined by these concrete elements. What else do we have here? We also have a small portion of unreinforced masonry, and the city of Quito has this colonial neighborhood. It has this El Centro Histórico, they call the historical center of the city, which still has a lot of buildings made of unreinforced masonry, made of adobe, made of clay bricks, which are of high value to the city. This is the cultural heritage of the city, but they are very old. So this is construction that can be particularly vulnerable to earthquakes. So today we want to evaluate risk for the whole city, and we're going to see the effects of the seismicity in the different neighborhoods of the city. This particular neighborhood, the Centro Histórico, might have a concentrated risk because most of the typologies in this or the building classes in this particular region are non-ductile, are very old structures, are not ready for earthquakes. So it's important for us to take that into account. And that's what we want to do today. We want to explore how risk, remember those questions that we were asking, who is more affected by risk? Which parts of society are more affected by earthquakes and why? This is what we want to do today. We also have some reinforced concrete high stories, like tall buildings also in the center. This is the capital of the country. We also have these high-rise buildings in the city. What else do we have today? Today, we're showing you a very nice feature of OpenQuake. In previous sessions, especially in the second workshop, I was telling you that there must be complete agreement between the building classes that I have in my exposure model and the vulnerability curves. Basically, there has to be a one-to-one agreement. If I have unreinforced masonry in my exposure, I need to have an unreinforced masonry vulnerability curve in my vulnerability functions, okay? So we have to have that one-to-one agreement. And it was like that initially with OpenQuake. But as the engine evolved and as risk assessment techniques also evolved, usually we can have now in the exposure model, because the exposure modeler started to model the city, and let's say that particular person decided that in the exposure we can have 10 building classes, but we can have, for those 10 building classes, sometimes we can have less than 10 curves, or we can have more than 10 curves. What do I mean by more than 10 curves? Look at this example right here. This is what we call a taxonomy mapping file. In the taxonomy mapping file, we can see that this is the building class that was found in the exposure, the one that says taxonomy. This is the building class of the exposure. And conversion is the fragility or vulnerability curve that I want for this building class. So I can see that for reinforced, for infill masonry, so masonry infills confined by concrete elements of 2 stories, we have a building curve whose name is not exactly the same one. You can see this is following the GEN taxonomy. This is following a different taxonomy, okay? So now we are violating that golden rule that they have to match one-to-one. Through a taxonomy mapping file, we can say, this is the taxonomy in the city of Quito. This is the building class in the city of Quito. And this is the building, the building class or vulnerability curve that I found that matches the most this building class. And this curve can come from a risk modeler, it can come from academia, it can come from research. I may have found it somewhere within the academic circles. Wherever I found this curve, it has a different name than mine, than the building class in Quito. But I can do through the taxonomy mapping file a one-to-one conversion. I'm telling the engine, this is the taxonomy in Ecuador, this is the taxonomy in the city, and this is the taxonomy that I have in my vulnerability curves. So now we're violating that rule through the taxonomy mapping file. Okay, so the taxonomy mapping file allows us to map what we have in the city to what we have in vulnerability, and they do not necessarily need to be one-to-one. Moreover, and important, it also allows us to give a weight to that map. So basically, what I'm saying here in this first building class is that the taxonomy the building class that I found in the city is 100%. I am 100% sure that can be linked to this vulnerability curve that I found maybe somewhere else. And it's the same for this building class. It's the same for this building class, unreinforced masonry. It's the same for 1 and 3 stories. It's the same for the adobe. So all of this, I am linking them to a single curve. But this is where it gets interesting. In Quito, the modeler decided to group all the buildings of between 11 stories and 20 stories of reinforced concrete. That person grouped everything in a single building class. But in the literature, in the academic circles, through a risk modeler, I was able to get my hands on 4 different curves for this type of class. One for 11 stories, one for 14 stories, one for 16 stories, and one for 20 stories. It means that now I can say, before I had to choose which one of these will represent this building class of the city. But now I can actually choose the 4 of them to represent the same building class in the city. And I can give a different weight to each one depending on my confidence on how much this building class resembles each one of these. So for example, here the modeler says, okay, I group all my buildings from 11 to 20 stories, and I am giving 70% of the weight to the curve that I found in the literature for 11 stories. 70% for 11 stories, 20% for 14 stories, and 5 and 5 for 16 and 20. These weights might be reflecting my confidence in these curves. They might also represent my knowledge about this building class. Maybe 70% of the buildings are in 11 stories. So or from 11 to 13 stories. So I put 70% in this particular, then 20% in this particular one, and so on and so on. What I am saying, most important thing about the taxonomy mapping is that we are no longer limited to a one-to-one in our exposure building classes and our vulnerability building classes. Now we can link them through the taxonomy mapping, and we can assign different weights if I have different building classes that can represent different vulnerability curves that can represent my building class in the city. So I hope this was clear. It's a very nice tool. It's quite nice because usually this is the case. Usually we use a taxonomy, a certain taxonomy, let's say GEM taxonomy, but then I found a HASUS curve that I want to use, and it's in the HASUS taxonomy, so I can link them, I can map them through the taxonomy mapping file. So it's a very neat feature to have. The taxonomy mapping file is a link between the exposure taxonomy and the vulnerability functions ID. So if there are no questions regarding that, I think it was pretty clear. What are we going to do today? Right now, you can see it. I am running an event-based calculation. Actually, I am checking. My calculation already finished. My calculation finished in 477 seconds. So you can let us know in the chat. So, Ale, 400 seconds. You can let us know in the chat for our knowledge. How long did it take your calculation to run? If it's done, if it's still running, you can tell us it's still running. But let us know more or less what is the average, what was the number of seconds that were required for your calculation. Right now, my calculation took 477 seconds, okay? Why does it take so long? It's because, remember, now OpenQuake is doing a stochastic event sets. We told OpenQuake there is an investigation time that I want for seismicity, and it starts year by year generating ruptures. So it's generating ruptures. It goes through the whole process of generating ruptures, and this is what we're going to see today. One of the first outputs that we will see today is the earthquake catalog, and we will see that earthquake catalog, and we will be able to explore this particular rupture, what magnitude it is, what type of event it is, what tectonic region it is, etc. Nice. So ruptures are the definitions. Ruptures are fully defined. They have magnitude, deep, breadth, and strike. But we also have a PSHA model, and we will see that indeed we have a PSHA model. In that PSHA model, we have a logic tree with GMPs, which allow us to move from this to ground motion fields, and the ground motion fields to losses through the vulnerability relationships, right? So I can see Henry already finished. Wincel is still already finished. Kata already finished too. We are also going to explore the event loss table today. So perfect. We are also going to see the aggregate loss curve, and we will see that we can ask OpenQuake to give us the mean curve, or we can OpenQuake to give us the curve for each realization as well. And last, we're going to see the economic losses. So we are going to generate economic loss maps. So this is what we will be doing today. I am going to abandon the presentation now because even though my calculation is done, I'm still not going to go and see the results. I want to show you the configuration file of an event-based risk calculation. And we can go through each parameter of the configuration file. So where is the configuration file? I am leaving the presentation, okay? I am leaving also the QGIS. I'm not gonna go to QGIS. I am going to go to my folder of today's exercise. I double click on the folder. And very good. I am opening right here. So this is today's exercise material. If I go into the event-based risk folder, just double click there, and you will see that we have all the outputs here, all the inputs here for our calculation. Remember that there is no difference between a PSHA calculation and an event-based calculation. In terms of inputs, you need the same PSHA model. You need the same classical PSHA components. And just to demonstrate that, I will go into the hazard folder so you can see that here in the hazard folder. Let me make this bigger. Indeed, we have a source model. Indeed, we have a logic GMP logic tree, and we have a source model logic tree. So you can see that within the inputs of an event-based risk calculator, you have the same PSHA components. We saw these components with Kendra, so I'm not going to go into this. I just wanted to show you that indeed we are using a source model today. So the ruptures are being generated from a source model. And today we also have everything required. You can see that the taxonomy mapping is here. If you're curious later on, maybe after the workshop, you can double click in there and see what's in there. You can see we're providing a site model with the site soil characteristics. We have talked about this in previous workshops. And we also have the keto exposure model. I'm not going to open it because we already talked about the exposure model in the module 2, in the second part of module 2. Very good. So I am not going to go into this because we have seen it in the past. What have we seen? The job ini file for an event-based calculation. So I'm going to double click in the job ini file, and you can do the same because we might do some things here. So just so you can follow me, double click in here, open the job ini file, and we will be able to explore the job ini file together. So here are all the parameters that we're asking OpenQuake to use for the calculation. So let's check the first parameter. Just like when we were using the IPT, the first parameter is the description. So this description is telling me that this is an event-based risk calculation for keto. Important, we are having 100 stochastic event sets. So we're asking OpenQuake, please repeat the simulation of seismicity 100 times, okay? And we are having 10 samples of the logic tree. And this is a new parameter that I will explain later on. When we're seeing the particular parameter, I will explain what this means. But the description, quite explicit, event-based risk calculation, the length of the set, and the city where I am in. So everything quite clear. Calculation mode, today we're using event-based risk, okay, calculation. So perfect, we have for the calculation mode, event-based risk. It's basically specifying OpenQuake which calculator we want to use. So this is not classical PSHA. Today we're doing portfolio risk, which means we need an event-based approach. This parameter aggregate by is quite nice. Remember that our exposure has different tags, and those tags are additional information that the exposure modeler gathered in order to disaggregate risk. I can do the portfolio risk assessment per tag. So remember that if in one tag I had a particular type of client, I can disaggregate the risk by that client. I can disaggregate the risk for the construction material, for example, for the taxonomies. I can disaggregate risk for anything that has a tag. Today, in this particular case, let's disaggregate. Let's aggregate our risk by let's say parroquia. So I am going to erase this. You can also erase this. Let's do the aggregate by parroquia. What is parroquia? Parroquia is the parish, is the word for parish in Spanish. It means that today we will do portfolio risk assessment, right, for the entire city. But we can also do it per parish. So we can ask OpenQuake, because I have attack for each asset in my exposure. I know in which parish it is. I want to aggregate the risk per parish. So I am doing a risk assessment per parish. This is quite interesting because it means that, for example, I was telling you about the Centro Histórico and how important it is for the cultural heritage. So I can do risk assessment per parish and see what is the risk portfolio for the portfolio in the Centro Histórico. So let's do aggregate by NM parroquia, just as it is right here, NM underscore parroquia. This is the tag that is in my exposure model, and this is the exact name of that tag in my exposure model. Very good. So I am not going to explain this parameter, ignore master seed equals true. Right now, we won't talk a lot about, I won't go into the aleatory process of that the engine does. Let's talk a little bit about the exposure. So exposure file, we are providing you with an exposure file today. So you can see there is an exposure XML. You can see it right here. Exposure XML. If you're curious, you can double click in there and see the file. We have explored exposure models before. I won't stop there. The taxonomy mapping. Indeed, we have a taxonomy mapping file. So taxonomy mapping CSV is this one right here. And remember that taxonomy is basically linking the building classes in my exposure with the IDs of the vulnerability curves. That is that link between them two. Vulnerability. Do we have vulnerability? Yes, we have structural vulnerability. In other words, we will be able to estimate losses in the structures because we have a vulnerability file for the structural components. And interesting, we also have occupants vulnerability file, and you will see it right here. You can see that we also have vulnerability fatalities XML. We are providing you with that file today. It means that today we will be able to estimate fatalities. Unlike the previous time where we didn't have that function when we were doing the exercise for Medellin, today we have an occupants vulnerability file, which means that we'll be able to estimate economic losses and human losses. Important difference, today we're not using fragility. So we won't be estimating damage. And we are not using a consequence model together with fragility. We are going straight to losses, okay? So today we are going straight to vulnerability, economic losses in the structures, and human losses in the structures, okay? So this is what we will be calculating today. So obviously today we won't be able to do damage maps. Today we'll be able to do loss maps. Site model file, we're providing a site model uniform grid. So basically we're providing a grid of points where we have BS30 data, and OpenQuake will use that BS30 together with the GMPs to amplify the possible intensity that I can feel in the surface, the ground shaking intensity. Okay, now we're getting into very interesting things. So the ERF and the ERF parameters, you saw them with Kendra last time. We have the mesh spacing. We are going to keep it at 5 kilometers. We have the complex fault mesh spacing. We're going to keep that at 5 kilometers too. We also have the width of the magnitude of the beams that we want, how we want to discretize the magnitude beams in our magnitude frequency distributions. We are discretizing by 0.1. So basically, we will be sample events from 6.0, 6.1, 6.2, magnitude 6.3, etc., etc., etc. So we are discretizing the kind of ruptures and magnitudes that we can have. And we also have the area source discretization in 5 kilometers. So everything quite clear up to now. Do we have logic trees? Yes, this is an event-based calculation, which means we need the PSHA inputs. And we have a source model and a source model logic tree. And we have a ground motion model, a logic tree, with all the ground motion models that we will use for each different tectonic region type. Very good. We have seen all, up to now, nothing that we haven't seen in the past or that we don't understand. This is where it gets interesting. So hazard calculation parameters. So this is an event-based risk, which means OpenQuake is expecting from the user the length of the stochastic event set. So how much is the stochastic event set? How long is the stochastic event set going to be? How many years of seismicity do you want to simulate? In the engine, it works like this. That is not a single parameter. I just don't input 10,000 years. I will explain to you why. We have split this parameter in three. Okay, so the first one is the investigation time. It's basically what is the size of the time span for each stochastic event. In this case, 1 year. So basically, we will be doing sets of 1 year of seismicity. Okay, so 1 year, 1 year, 1 year. And in sets per logic tree path, we are asking for 100. Okay, so we're saying we have 1 year sets, but I want you to do them 100 times. Okay, so we're going to have 100 sets of 1 year seismicity. Okay, very good. That effectively, so far, we're asking OpenQuake to make 100 years of seismicity. And here's the third parameter, which is also important. What are the number of logic tree samples that I will take from the logic tree? Okay, so basically, what does this mean? Basically, we are asking OpenQuake to do an stochastic event set also per branch in the logic tree. So I am telling OpenQuake through this parameter, sample 10 branches of the logic tree. Okay, so only use 10 branches of the logic tree. So basically, we have 1 year sets, okay, 100 times 10 branches, one for each of 10 branches in the logic tree. So far, my investigation time effectively is 1,000 years, okay, because it's 1 year seismicity, 100 times 10 branches of the logic tree. That's 1,000 years. Perfect. But why so complicated? Why did we split the calculation parameter? Why can't it be just one parameter? And the answer is computational demand. Is actually what we were getting that question in the chat before. Why do we want to split the parameter? We want to split the parameter because it makes the calculation more manageable, okay? There are logic trees, and I'm pretty sure Kendra mentioned this, but there are logic trees that can have thousands of branches in the logic tree. So imagine what it is to ask OpenQuake to make a simulation of seismicity for 10,000 branches of the logic tree, and each one of those repeated 100 times. So the calculation can get out of hand very fast for big source models, or for PSHA models that have big uncertainties associated to them. So we need to ask OpenQuake to disaggregate or to compartmentalize. I don't know how the word would be in English, but we want to ask OpenQuake to do the calculation only for particular logic tree branches, so it is manageable, so we can finish the calculation. So my stochastic event set is of a size that is enough for the risk assessment, but not so big that my calculation or my computer cannot make it. What if I want, and this is the last comment, and then I will ask if you have questions, but what if I want, in any case, I want an stochastic, I want 100 stochastic event sets of 1 year for every simulation, for every logic tree in my PSHA model. Basically, I want to consider the full uncertainty of the PSHA model. So instead of putting 10 here, you just have to put 0, and 0 means full enumeration of the hazard logic tree structure. So basically, you are going to do 100 stochastic event sets of 1 year for every branch in the logic tree. So if there's just one branch in the logic tree, then your set would be just 100. If there is 10,000, there is 10,000 times 100. So your stochastic event set will be very big. So this is how you manage the size of your calculation. Another key question is that we always get here is like, well, if my logic tree is very big and I cannot put 0 here because I'm running my calculation in a laptop and I don't want a huge stochastic event set, stochastic catalog, then what should I put? Is 1 enough? Is 10 branches enough? What about 20 branches? What about 15? What about 100 branches? What is the appropriate number of branches? The appropriate number of branches is the number of branches that allow you to sample as much of the uncertainty as you possibly can. Okay, so in this case today, because this is again an academic exercise, we're sampling 10 branches of the logic tree. But if you feel that 10 branches aren't enough, there is a way of either increasing here, you want more branches, or you can run a calculation and then ask OpenQuake to run another calculation with other 10 branches and so on and so on and so on. So the calculations are manageable in size, but you can repeat them on and on. And then you have different sets of risks that at the end you have to combine, okay? So this is how the length of the set, the length or the size of your stochastic catalog is handled by the engine. And this is how we handle it through these 3 parameters. Now, is there any questions? Was this not clear? Let me know in the chat. So let me just go in the chat to see what questions we have. Weihua Fang is asking, answer hazard distance is defined as the same for all ruptures in a job. Yes. Can it be separately defined for each rupture? No, because how many ruptures are going to be sampled? You don't know that beforehand, right? It will be hundreds of thousands of ruptures. So you don't even know how many ruptures will be sampled by the engine. How many depend on the seismicity of your region. So it's very difficult to know this beforehand, so you cannot define that per rupture. Here is asking, I run one CES for 100 years and also one CES for 100, I run one CES for 100 years and also 100 CES for 1 year. All things equal, I get the same result. Yes. Does it mean the results are stable and that I no longer need to try 1,000 CES? No, it doesn't mean that. Try 1,000 CES and see if the calculations are different. If 1,000 CES is giving you different risk than 100 CES, it means that your risk metrics have not converged. So it's true what you said, that there is an equivalence between one CES for 100 years and 100 CES for 1 year. Those are the same, but your second calculation is much larger. You're considering more ruptures, etc. So if when you analyze the risk, you get different average annual risk metrics, it means that you haven't converged in your risk. You need to use more CES. I hope I was able to answer that question well, Henry. Okay, perfect. It seems that it was clear. Conrad, you're telling me that your calculation failed. Please share with us in the chat or directly to Kata what happened with your calculation. It can be a memory error. These calculations are very intensive. So to see a calculation error or how did it fail is very simple. You go to your plugin. So let's go to QGIS. Okay, we go to our plugin. We click on the play icon. Okay, and we go and we see the console. Okay, we can see here mine is complete. In your case, Conrad, it should say failed. You click on the console. Let me see if it opens the console. Yes, and here you should have all the log of the calculation. So it tells you which OpenQuake version you have, etc. Interesting here, look, this comment, considering 10 logic tree paths out of 54. So because I sampled 10, I'm taking only 10 branches out of 54 branches. So now we know that our PSHA has 54 total branches, our PSHA source model. So Conrad, go all the way down and please, you can send to Kata, copy the error message that you're getting and send it to Catalina in the chat, or you can even send it in the general chat to see what is going on with your calculation. If anyone's calculation fails, please let us know too. I'm going back.
And then we have another question.
Let me see. Minimum, okay, so Weifa has a question about the minimum intensity. Because I haven't talked about this, let me just go through the parameters, and if at the end this question doesn't have an answer, we can go ahead. But I hope it's clear. you understand the size of the stochastic catalog. You understand that there's a very good reason why this is not a single parameter. It's for computational means to make calculations manageable. We have split this in different, three different parameters to input. And it's clear that in this calculation, the one we are doing today, we're actually doing 1,000 years simulation of seismicity for Quito, because we're doing 100 sets of 1 year for 10 logic trees, logic tree branches. So in total, 1,000. Very good. Truncation level, yes, we want to consider the uncertainty of those GMPs in the ground motion fields. So truncation level 3. So we're truncating basically at the tails of the Gaussian curve. Answer hazard distance. This is very important parameter, and I don't think we have seen it in the past. Answer hazard distance, what does answer hazard distance mean? Answer hazard distance allows you to, if you have a building, okay, and in the BS30 grid that you provided, it has BS30 sites in the city. But if this particular building is not in a particular site, it's not exactly on top of one of those sites, OpenQuake will grab the BS30 from somewhere else, okay? It will grab it from a close by region. So we can tell OpenQuake, grab the quality of the soil from a close by region. How close? In this case, it says 250 kilometers. This is wrong. We don't want to do that. We don't want to take the BS30 for this building from a site that is 250 kilometers away, because it means that we are not actually taking into considering the soil in this site. We're considering the soil in a completely different site. So 250 here is conceptually wrong. You need to change this to 1, or even less if you want. OpenQuake will raise an issue if, for example, here I'm saying 1. OpenQuake will raise an issue if there is, I have a site, it has buildings, and there is no BS30 values within 1 kilometer. I will see it in the calculation. OpenQuake will complain, will say, you asked me to grab information when I don't have it available from 1 kilometer, but I didn't find it in 1 kilometer. And OpenQuake will give you that warning. So this is quite interesting. It's a very important parameter. And one question that we always get is like, why is this so complicated? Why can't you just have the BS30 below the building and then OpenQuake doesn't need this parameter? Well, when you model risk, in this case, for example, you have a city that has 3 million people. And if you did a very good job in your exposure model, then you have buildings everywhere in the city. But maybe you don't have information for all those buildings, right? You don't have the information for all those sites. So maybe you just have certain sites. Maybe you just want to simplify and say, okay, this is the limited information that I have. Please use this information. OpenQuake can do that, but we need to then tell OpenQuake what is our range that we want to use to grab information from different sites, okay? So remember that these parameters exist to make the calculation possible, to make the calculation even with limited information or the information that you have to make the calculation possible. So again, this was originally 250 kilometers. Let's change it to 1, okay? You can put it into 1. This is already a change, so save this calculation and you can run it later on. Again, so far so good. Is there any question regarding anything of this? I think it's quite clear. The catalog size, which is the key concept that we have to have clear, I think is clear. So let me just finish talking to you about the different filters, and then we go on to see the results of the calculation. It seems that only Conrad had a failed calculation. If anyone else had a failed calculation, let us know. But okay, perfect. So now we're going to the risk calculation parameters. For risk, we want a risk investigation time of 1 year. In other words, we want the average annual risk metrics, okay? If you put here 2, you will get the average risk biannual calculations, risk results, let's say. Basically, you can ask OpenQuake how to normalize the calculations. Usually in risk assessment, we go for the year. We want to understand the average loss every year that the portfolio has, or that the portfolio can present during this entire period of seismic. So the investigation time here is usually 1. Minimum intensities. So we have certain filters, since these calculations are big, they take time. We also, OpenQuake also has certain filters that might make the calculation more manageable for the engine. For example, minimum intensity allows you to discard ground motion fields whose intensity is so low that they won't cause damage, and then we discard them right away. OpenQuake doesn't even do the intensities times the loss ratio to see if the loss is very low. No, with this filter, if the ground motion fields have intensities, for example, for PGA below 0.05, the ground motion field gets discarded. For a spectral acceleration below this, discarded. Below this, discarded, and below this, discarded. It means that we are making the calculation easier. Since there are thousands or hundreds of thousands of ruptures during our investigation time, we just want to use the ones that are important, the ones that can be damaging. And so we're discarding here the ones with certain intensities that are too low to be considered here. We can also discard from our event losses, losses minimum to something. So for example, here we're discarding every loss that occurs that is less than $500. If it's less than $500, let's discard it from the list. We can also do the same for the occupants, but for occupants, usually the loss of one occupant is very important. So usually for occupants, we just set this to 0 because we don't need a filter for occupants. Maximum distance, we can also filter out events that are occurring too far away, and hence they might not be interesting for my region. For example, subduction interface events filter out more than 400 kilometers, more than 400 kilometers away. Active shallow crust, 350 kilometers. So basically, OpenQuake starts sampling things. If this is too far away from, according to this filter, should be out. So it takes it out, and then hence the calculation is more manageable. And the same with magnitudes. We can do a filter for magnitudes. So we filter out magnitudes that we know won't be damaging or are not interesting for us. This is important because remember that magnitude 4 events, for example, will happen very, very frequently according to the magnitude frequency distribution. But most of them are not damaging. So we want to filter out that. We want to save that time in the calculation. We don't want OpenQuake to lose time sampling those ruptures, checking them, discarding them, etc. So we can just filter out certain magnitudes right away, protect only region type. Okay, perfect. That's why it meant. Did I answer your question? And let me just go back to the chat to see what is the question. You were asking in the chat. So minimum intensity is used to reduce the computation needed by PGA value, or PGA value defined here is simply by removing unnecessary PGA values in ground motion fields. It's what I was saying. Like the PGA, if you have a filter to filter out ground motion fields whose intensities might not be damaging, basically. I hope that answered your question. Very good. So I can see that most people finished their calculations. Some took 500 seconds, some took 1,000 seconds. But it's good to see that all of you managed to finish. You're welcome in the chat for the answer. Let's go check the results. So this was it. Through this, we basically saw everything that was important to see in the parameter input file in the job ini. So let's go back to our QGIS, and you can see that my calculation right here has finished. So it's complete. Okay. I'm going to click here on my calculation because it's complete. Is this one Quito event-based risk says 100 NLTs equals 10. So 100 stochastic events of 1 year times 10 a number of logic tree samples. Perfect. Event-based risk calculation. You click on outputs. You click on the calculation when it's blue, and then the outputs will be displayed right here. So you can see my outputs are right here in You can see there are many outputs, okay? I will show you the 4 outputs we talked about during the workshop. So the first one is, let's check the stochastic event set. Let's check the catalog of ruptures that OpenQuake sample. So it's actually this one right here. You can see that there is, in mine is the ID 58, might be different in your computer, but it's the one called earthquake ruptures. And this is a geographical layer. You can see you can load a layer, or you can download it as a CSV or an XML file. So let's load the layer. You can see here that the QGIS plugin also allows you to filter out certain events if you don't want them to populate your QGIS, or so they are not such a huge catalog in the visualization tool. So I said load layer. It takes a while because there are many events. Let's check. So here you can see there are many ruptures in this file. So you can see they come from with different color. In this case, the color, I asked for the color to be according to the tectonic region type. So you can see the active shallow crusts are actually this celeste, this light blue color. The yellow ones are the subduction intraslabs. You can see that all the subduction intraslab events that are occurring here. And you can also see the subduction interface. Basically, in the converging zone, you can see that there are also some events occurring right there. If you are interested in exploring each one of these events, you can do it either through the table output. You can even do it through QGIS. You just click on the identify features icon, which is the white eye with the mouse icon, and then you can go to a particular rupture, and there it is. We have everything defined in this rupture. We have the rupture ID, we have the multiplicity, we have which magnitude it is, the location, we have also the depth, the tectonic region type, the deep, the strength, and the rate. Quite neat. Why? Because we know there is a risk associated with this rupture. And if it is a risk that is important to me, if, for example, I went to check all the events that are have a 500 return period, because maybe 500 return period is important to me, I have that information. I can see it here. So I can just grab this rupture, and then I can do different analysis with this rupture. Maybe I can do a scenario assessment with this rupture, just like we did before. And maybe I can ask OpenQuake to give me more ground motion fields for this rupture, etc., etc. So it's quite nice to have all the information about the ruptures here. It's quite nice to see everything here in the QGIS as a GIS file. But remember that there is also a table to this output. First output of the event-based risk assessment done. So we have seen the ruptures. Quite neat. Now we're going to move on. I'm going to go back to the plugin. Second output that we saw, aggregate loss table. Okay, so let's see the aggregate loss tables. Okay, so I am going to click on my calculation, and I am going to see let me see, aggregate loss statistics, aggregate event losses. Okay, so my aggregate loss table, this is a table. I click on load it, and here it is. This is my aggregate loss table. This is the table that I told you that for each rupture contains the risk of each rupture, the losses, economic losses, and fatalities. And the first thing that you will say is, well, this is very different from what you were showing me in the presentation, right? Because in the presentation, you were telling me that you have the magnitude, that you have the location, and you have, that information is not here. You can see that we have the event ID and the risk that it costs, the number of occupants, and the structural damage. But what is this? What is the rest of the information? I can see here that at least the year where it was sampled is here, but where is the rest of the information? For your convenience, and believe me, for your convenience, we do this, the information about the rupture, it's in a different file, okay? But you can access that file through the rupture ID. So as long as you know the rupture ID, and in this case is the rupture 4, I go to the file and I look for the rupture 4, and I find everything, the magnitude, the deep, the rate, strike. You can even find the full geometry of the rupture. This polygon right here, you can find it in that file. So we separated the files so they are manageable in size, because that table is huge and this table is also huge. Okay, so it's important for you to know that this is the aggregate loss table that I was showing you in the presentation. It's just in a simplified manner. But right now, you can do the same. You can, for example, you can see which is the rupture that causes the most losses. You can see here occupants. This particular rupture, 2,848 sample in the first year of seismicity actually is the one causing the most economic losses. And it's the one causing a lot of injuries too, okay? So here you can sort the table, see all of this. You can even do it manually if you're ever interested in arriving to the inputs by yourself. Right now, OpenQuake did all of this for us, and it already reported for us the aggregated risk for the portfolio. So this is the aggregated risk for the portfolio. Very good. This is the second output of the event-based risk that we were going to see. We already saw ruptures. We already saw aggregate loss table. Very good. Third one, curves. So probability PMLs, maximum probable loss exceedance curves. We can see them going back to the calculation, making sure the calculation is highlighted, and then we can see the aggregate loss curve statistics. This is the one that we want. Aggregate loss curve statistics. We click on show, and here it is. Let me show you right here. Let me get rid of this one too. This is the curve for my my portfolio. So basically, for all the years that of seismicity that I have, OpenQuake sorted the table, got the rank of each rupture, calculated the annual exceedance of each rupture, and also calculated the return period of each loss. So sorted the table, got the losses per rank, calculated the average annual exceedance of each of the losses and the return period of each of the losses, and it builds this calculation, this curve right here. What is the neat thing about this curve? Remember that I told you that we were aggregating by parish, by paroquia. It is right here. You can see that we have the mean statistics for the parish of Centro Histórico. So we have because I asked OpenQuake to aggregate by parish. We have the risk aggregated, and I can see not just for the Centro Histórico. I can see the risk in any portfolio of any of the parishes that I want. So I just go to the parish and I click on it, and I can see what is the portfolio, the portfolio curve for that particular parish. So it's, remember that tags are quite useful when you want to disaggregate risk by different types of tags. So in this case, by parish, you can do it by material as well. You can do it by any tag that you put in your exposure model. You might be wondering now, well, I don't want it for paroquia. I don't want it for material. I just want one curve for the entire city. It means that you have to come here, and what you need to do is you need to comment out this parameter. So you comment out the aggregate by parameter, and you will obtain a single curve for the city. Okay. So this is quite important. You can just save this calculation and rerun it, and you will see that you will no longer have the possibility to disaggregate or to see the risk curve per parish. You will just have one for the city. I also said that we could obtain different curves for different for each realization of the logic tree. And if you remember correctly, this time we asked for 10 curves. So why do we have only the mean curve? Why do I have only the mean results? I only have the mean results because I didn't specifically ask OpenQuake to give me the results disaggregated by branch. But you can do that. How do we do that? I'm going to show you. You go back to your calculation, change the description so it is differentiated from this one that we do. And we're going to say in the visual curves. Okay, so in the description, I already said that my next calculation will be for individual curves. Okay, but I have not provided the parameter for individual curves. The parameter is individual curves equals true. And with individual curves equals true, you just click save, and then you run this calculation. Its name will be different from the previous one because this one is called individual curves. And what you will obtain is basically this. Instead of seeing this single curve, you will be able to see the curve per realization of the PSHA logic tree. Okay, so I highly encourage you to try this, to try to do it on your own if you can. I will see if I can, maybe I can leave this particular job running right now so we can see the results at the end. Very good. So what am I going to do now? We already saw 3 outputs. The last one, the aggregate loss maps. So basically we can create a average annual loss maps with this calculation that we do. Because we provided OpenQuake with a vulnerability model for structural components and also a vulnerability model for fatalities, we will be able to compute economic losses per each asset, and we'll be able to compute occupant losses or fatalities for each asset. But we can also construct a map. In other words, aggregated by zone and present the risk, the average risk by zone, any zone, administrative zone that we choose. For Quito, we can present it by province, but it makes no sense because we would only see one color. Since we have the risk by neighborhood, let's present the risk by neighborhood. Let's explore the risk by neighborhood. So how do we do that? We are going to click on play icon again to bring the interface, and we are going to make sure that our calculation is selected, and we are going to go to average asset loss statistics. So average annual losses, annual because we chose one, my risk investigation time, and we're going to click on load layer. Okay, so when I click on load layer, I will be able to bring a layer just like we have done before with geographical information. So it's going to bring you this little window. This window allows us to choose what we want to plot, choose what we want to map. So what am I mapping? I'm mapping the mean realization, the mean realization. So this map will be representative of the mean risk. I can choose for which building class I want to do the map. So I can see here by taxonomy, I can choose a particular taxonomy. Let's check, why don't we choose unreinforced masonry of Adobe, okay? Because I am interested in what is happening in the Centro Histórico, and I know the Centro Histórico is built with this particular building class. Is made of unreinforced masonry. And I am interested as a risk manager maybe to explore the risk there. Let's make a map of this, and we are going to choose whether we want to see the losses of the occupants, in other words, fatalities, or the economic losses. Let's choose the occupants, okay? And if I remove the aggregate by zone, OpenQuake is going to bring me the risk per asset. So I'm going to see points in my map file, right? But let's not see points in the map file. Let's aggregate all the points that we have per neighborhood. So we explore the risk per neighborhood. And we're going to click, sorry, let's do it by parish. So I know the Centro Histórico is a parish, so I'm interested in that parish. Let's do it by parish. You can also do it by neighborhood if you want. Just choose whatever you want and click on OK. And this is going to load you the map. So I am going to remove the rest of the things that I have so I can explore my map. But you can see here, this is my risk map, okay? So basically, I am seeing here the losses by, I am seeing the losses, the average annual losses per building in the specific unreinforced Adobe building class per each of the parishes in Quito. Some of you might be wondering, well, the losses are very small. I mean, why is it so small? Remember that this is annualized. Is the sum of all the losses divided by 10,000 years. So the average risk metrics tend to be small, for example, in the terms of fatalities. So this is why they are small. And now I can explore what is happening in the Centro Histórico because I can, having highlighted this layer, I can just click on this. and show me what is happening in Centro Histórico. And this is the results. So I basically have the results for, let me just hide this so we can see very well. I know what is my average annual number of fatalities in Centro Histórico for this particular zone in this particular parish, okay? I can also see that there are some other parishes that have higher risk as well. So I am interested in the cultural heritage, yes, but through this map, I am finding out that there are other regions that also have this very vulnerable type, unreinforced adobe, and in even greater numbers, and hence they are also in high risk. So for example, this region called Tumbaco and this region called Calderon, they are also in particular risk for this, given this particular building class. So this is how we explore risk, and this is how it can be very useful for risk managers. Because it means, for example, I was very focused on Centro Histórico because it's cultural heritage, right? Well, this map is telling you that there is more, that there is more adobe there's more unreinforced buildings in my city that I might have been unaware of, and then it's expanding already my knowledge of the risk. It's making me understand where the risk is, and these kind of maps are quite useful for making decisions about retrofitting, about any long-term mitigation strategy. Let's try to make another map for economic losses. So we know we're seeing right now which are the parishes that have the most average annual number of fatalities. Let's unclick it and let's do a map of economic losses. So we're going to click here, make sure that this is selected. And I'm going to go again to average asset loss statistics. I'm going to load a layer, the mean realization for all building classes this time. And I'm going to choose structural, okay? And I am going to choose neighborhoods this time. So I choose the neighborhood. I click on OK. And this brings the losses by neighborhood. So you can see here which neighborhoods are concentrating the most economic losses in terms of average annual losses through all my period of size visit. So basically what I'm seeing here is which neighborhoods are losing more money in absolute terms, through my period of size visit. So again, you can explore this map and you are going to, you can click, for example, I want to see this particular neighborhood. Is the neighborhood of Carapungo. And I can see that this neighborhood has an average annual loss of, let's see, $1.4 million. So that might seem low in comparison with what we have done before, because before we were doing a single scenario. So we were seeing the consequence for a scenario that was happening. So we were seeing thousands of losses, thousands of collapses, things like this when we were doing the previous exercise. These are in average risk. When we're doing average annual risk, you will see that the numbers are much smaller because it's the entire loss divided by my investigation time. So I understand which one is losing annually according to my simulated seismicity, economic losses or fatalities. So this is basically the map that I was showing you before, and the map, this kind of maps again allows us to understand where most economic losses going to come from, and hence if my interest is to mitigate economic losses, then I can use this map to understand where I should focus my efforts.